Hello, my name is Emilio Artacho, and I'm going to tell you now about how to get basis sets for Siesta. Starting where we left it off before, Siesta basis sets have to be made of atomic-like orbitals of finite support. They can be as many as you want, wherever you want, and of any radial shape. Let's see what Siesta can provide in order to generate good basis sets for you. Still, choices are yours, and how many, cutoff radii, where you put them, etc., are made by the user, but Siesta provides some automatisms in order to generate different kinds of basis sets. For instance, when choosing a D set P, it immediately understands that you want the right amount, a given amount, what understood by D set P, of orbitals in the different positions of the different atoms. And even if you don't say anything at all, it assumes a DZP. So if you want a minimal basis, then you would have to say single zeta, single Z. Now the radial shapes, they can be either introduced by the user as a table, so basis type user, or generated by Siesta. Siesta itself can generate different kinds of flavors of numerical basis sets, normally based on modifications of the numerical solution of the constant DFT problem for the pseudo atom isolated in space. They are quite tunable and depends on different parameters that you have to define. There are again various levels of automatism and the predefinition of default values for different parameters. Something very important I should say now, however, is that the tools that we're going to see that are offered by Siesta for generating basis sets are various kinds. You can get to basis sets of different levels of accuracy. You can have this mentioned hierarchical structure of defaults. And you can even generate the basis sets without your saying anything. But it is up to you to generate the basis you need. You're going to calculate for several, probably many months. Just spending a few days trying out basis and basis set convergence is really what we recommend, and actually what we do ourselves. It allows you to have much more control on the approximations you're performing on your calculations. Of course, people do share and can share basis sets. It is depending on trust, typical relations among scientists, and it can be done through communities. People share basis sets in the Siesta mailing list, for instance, but they can also be provided by third parties, like in the case of Simune, which is a company that offers service around Siesta, and they have they distribute basis sets. Anyway, let's start from the beginning, and that is the minimal basis. So if you have, say for instance, an oxygen atom, you would have for the valence electrons, you would have the 2s and 2p shells of orbitals. This would be an example of a p orbital, and here this would be the solution of an oxygen pseudopotential isolated in space under a strict confinement. So you put a hard wall, in this case at 5 Bohr distance from the center. That is an original idea by Sankey and collaborators, and they call these kinds of orbitals fireballs because they are excited. The fact that they are compressed raises their energy. And so we can start with that kind of thing. But with these fireballs, we have one cutoff radius per orbital. How do we define them? In that respect, there was a very useful concept introduced very early on, which is that of the energy shift. It is introducing one single parameter that defines how much the energy of the given orbital is raised when we confine it by the wall. And so that would define a relatively well-balanced set of cutoff radii. And you can see there just early convergence comparisons of the energy of different properties like bond lengths and bond energies as a function of this energy shift as a single parameter controlling the accuracy of the basis in terms of the cutoff radii, the scope of the orbitals. From that, we started to use soft confining potential because the hard confinement typically produces a discontinuity in the derivative at the kink at the end. And so soft confinement, it is illustrated here in the figure at the bottom. The vertical line there would represent the hard confinement we were using before, but instead of that, one can put a confining potential that starts at a given inner radius and then much more slowly diverges. And that you can see in the plots above it, that the kind of orbitals it produces. You can see the unconfined has a never-ending tail, but the continuous line represents an orbital that has been softly confined. You can use that kind of soft confinement automatically, and the default would be to have an inner radius for the startup of the confining potential at 90% of the cutoff radius. This is an idea that has been also used by other codes that came after Siesta. Okay, once we have the minimal basis, either so hard or softly confined, now we need to generate the further tiers, the further zitas, if you want, the further radial shapes of the other orbitals that we're going to introduce for radial flexibility. And there is a very traditional one, which is the one we started with, which is to use the excited states of the soft or hard confined pseudo-potential. And so that has very nice advantages. It is quite systematic. You don't need to do anything. The only problem is that it takes quite a few of them towards getting convergence, and calculations can get expensive. Actually, OpenMX, which is a code very similar to Siesta, that is using the Siesta method that was developed by Ozaki after Siesta, uses that kind of basis set as default. We can use it, but it is not our default. There are other options, other possibilities, and other codes use that. We can also use them, which is using chemical hardness ideas to generate the multiple zeta. That means using the derivative with respect to charging the atom. And that derivative gives us another radial shape that we can use to give flexibility to the atom to charge, uncharge, and deform as it is charged or uncharged. A further one, and this is the one we like most and we use more regularly, and actually it is the default, is our own version of the quantum chemistry split valence method, which is essentially to introduce different functions to reproduce different bits of the atomic orbital. In this case, very much tailored to Siesta and using an idea originally proposed by José Luis Martins, the same Martins as the truly Martins pseudopotentials. What we do is from the minimal basis, think about if you have a cutoff radius at the very end of the orbital, think about an inner radius, and Rm as a matching radius, and just take a function continuously, continuing smoothly from the tail inwards with a very, very simple expression like this inverted parabola there, matching value and derivative at Rm. And so once you've done that, you have two orbitals, two basis functions. And of course, since the basis set is non-orthogonal, it doesn't matter because we're dealing with the formalism of non-orthogonal basis functions. But even it can be done more interestingly. The same space is spanned by the difference between the two. So by the original single zeta orbital, and the second one would be the difference between that smooth curve and the original one. And if we then normalize it, then we have a double zeta for this original orbital. That's the way we normally do it. In addition, we can define at what radius we do the matching by, instead of specifying a radius per orbital, by controlling what would be the percentage of the norm of the original orbital we want to have on the tail. And that defines a matching radius for all of them. And the default value would be 15%. After having seen how to deal with radial flexibility in zetas, let's face angular flexibility. That's polarization orbitals. Here, what we show is two ways of generating it. One of them is by confining just the excited states of the free atom. That has the problem that sometimes the excited states of the free atom can be quite unbound or quite wide, and we might need them to be much more closer to the original radial shapes of orbitals they are polarizing. And so by forcing them to do that with the radius of confinement, you can see the kind of shapes we have in the curves on the right-hand side. Whereas on the left, you see much more sensible curves that have been obtained in a different way, following an original idea of José Soler, which were just by introducing an electric field actually in the solution of the confined atom itself. And that when you do that, any orbital shell will deform, incorporating perturbations from higher L angular momentum. And if you take those as the shapes you need for polarization, that's what gives you very sensible polarization orbitals. So all these things are introduced in Siesta in different ways, and there are a series of defaults. If nothing is specified that Siesta is going to take, for instance, the basis size is going to be taken by default as double zeta p. The energy shift, and here you have the commands that you can introduce in the input file to specify these things. The energy shift would be by default be specified as 20 millirydberg. The basis type would be the split for split valence. The split norm would be the 15% I was mentioning a moment ago, and the soft default would be normally false. So by default, it is a hard confinement. That gives you a pretty decent basis for many purposes in terms of accuracy versus efficiency, but it is up to you to see whether that's good enough for you or even too much for you. In my case, I normally prefer as starting point and default this kind of defaults, but I would go to a smaller energy shift. That means wider orbitals, and I would like to start with soft confinement by stating it true to true, which puts it by default at 90% of the original cutoff radius. One can have a much more direct control of all the parameters in the basis by going directly to a block in the input file, which is called a PAO basis. And within that block, one specifies many of these parameters. Here it is one only for hydrogen, but you can put a block like this, or pieces of this block for each one of the elements that you're dealing with. Here you have the hydrogen atom. Here the first one is to state how many shells are coming after this line. And you can even specify whether you want to charge the atom for the purpose of generating the basis. It has nothing to do with the charging of the atom in the system afterwards. It is just whether you want the basis of a cation or an anion, something like that. I normally don't use that so much. I don't like it, but that's personal. And then in the following line, you have the first shell, that's n equals 1. The 0 is angular momentum, so that would be a 1s orbital, and the 2 is a double zeta, 2 zetas. And then after that, you have the 5 and the 3. 5 would be the cutoff radius of the minimal basis, and 3 would be the matching radius of the second zeta. And with that, you wouldn't have a polarization. It would be just double zeta for this hydrogen. The last two numbers are optional, and they are scaling factors, which is something very traditionally used in quantum chemistry. So once you generate the basis functions, you can scale them, contract them, or expand them a bit. And that can also be done at this level. So there are many of these tools that you can use in order to generate your basis set. It can be from very automatic to quite detailed, and all the way to just your inputting a whole table of numbers. Regardless of that kind of thing, here we show you some results of convergence. This would be for bulk silicon, cohesive curves, so energy as a function of lattice constant of volume. For different tiers of basis sets, you can see how it works there. And you can see how it converges. It converges in the minimum and the curvature, so it would give you the lattice constant by the theoretical lattice constant, the bulk modulus, and so on. On the right-hand side, you can see how is the energy going down, the energy of the minimum going down as a function of the basis size. And it's actually compared with a plane wave cutoff calculation. So if you do the same thing with plane waves, and you put energy as a function of plane wave cutoff, here you have aligned where the different tiers of the LCAO defined by Siesta with the tools we're talking about before, that would be split valence and so on, how they compare. And the fact that when improving the basis, the energy goes down allows us to think about the possibility of optimizing the basis set parameters by minimizing the energy of some reference system close to the ones we might be interested in. There is a simplex utility in the Siesta package that allows you to do that in an easy way. But I would be careful with that. Blind optimizations can result in poor transferable basis sets. I prefer the strategy presented in the paper quoted in this transparency by Corsetti and others. Essentially, I use the variational optimization of the second zeta radius of the basis sets. Otherwise, there is, of course, the possibility of doing systematically on reference systems for the whole throughout the table, as done by and proposed by the code FHA aims. Simone has done that for Siesta by doing it on elemental dimers. And of course, please try to avoid using basis set parameters in order to fit properties. That is not what is meant to be done. Here you have also a little bit more general comparisons with a simple system that would be elemental solids from diamond, insulator, silicon, semiconductor, and 3 different kinds of metal: simple metal, a transition metal, and a noble metal. And you can see lattice parameter, bulk modulus, cohesive energy as different kinds of properties. And here you have a comparison between experiment, all electron calculations with TFT with our augmented plane waves. Then you have with plane waves and pseudopotentials, with our pseudopotentials and plane waves, and with our pseudopotentials and double zeta p. Those are the different columns there. So you can see how it changes from experiment to DFT, from DFT to having pseudopotentials, two different pseudopotentials, and from having pseudopotentials to having a double zeta, from having pseudopotentials and plane waves to pseudopotentials and a double zeta p basis. And you can see that the deviations between the different columns, the dzp as compared with the plane wave, gives you deviations that are very comparable with any of the other deviations in the table. So with that, I conclude. I have given you a general feeling of how to generate basis sets with Siesta and a tour of generating tools. And the key thing is that use them in order to get what you need.